So our next speaker is Boris Solomyak from Bar-Ilan University, and he's going to tell us on the spectral theory of deformations of self-similar tilings, eigenvalues, spectral cocycles, and Hölder regularity.
Thank you very much. So it's a great pleasure to speak at this conference in honor of Robert. I'd like to really thank all the organizers and also Bob for many, many things, particularly in the early 90s when I was still rather fresh arrival from former Soviet Union. Bob was so kind as to invite me to the Waterloo meeting in '95, which was really eye-opening for me when I met all the people in the quasi-crystal community at that time. And then we had, of course, an enjoyable collaboration with Bob and Jung Yup. I still remember how we were walking in the evening in Oberwolfach when we had the idea of the result about equivalence of pure discrete spectrum for pure discrete dynamical and diffraction spectrum. So I'm going to speak about the spectral theory of these deformations, but actually when preparing I realized that it's absolutely impossible to cover all of this. And in fact, spectral cocycle is something in the end will not really say much about. And I want to make this talk fairly non-technical. It's actually very serendipitous that Natalie just gave her talk, because many of the terms will that she used will also show up in my talk. Well, the goal is to investigate spectral properties of tiling dynamical systems, and we have already seen that was mentioned, I think, that diffraction spectrum is essentially part of dynamical spectrum, so this is relevant also for the theory of quasi-crystal for aperiodic order. In particular, when we talked about Bragg peaks in the diffraction picture, they correspond to the discrete point spectrum or the eigenvalues. Now, in the last, I don't know how many years, certainly more than 10 years, I was mostly interested in the continuous part of the spectrum because the Bezout conjecture seems incredibly hard. I couldn't say anything new in that direction, so I was focusing on the continuous spectrum. And in ergodic theory terms, continuous spectrum means weak mixing. But then it is actually of interest to understand quantitative behavior of spectral measures, namely how the measures of small balls decay when the radius tends to 0. Because well, saying that there is eigenvalue means that there is a point mass, and if there is no point masses, then the measure of the small ball goes to 0, and the question is how it decays. Now, so actually motivation for studying, and it is also comes under the term quantitative weak mixing. So the motivation for studying this question comes from at least two sources. One is the study of translation flows and interval exchange transformations, which is a very influential area in dynamical systems, in particular the work of Ivor Forney, who proved that almost every translation flow on a flat surface of genus at least 2 is weakly mixing. And then Sinai asked whether this weak mixing result could be made quantitative, or can we say that almost every translation flow is actually has Hölder continuous spectral measures. By now, this has been answered positively by Forney and then by Sasha Buffetta with myself by somewhat different method. In any case, and another is interest in singular spectrum, and this was also something that is also present in the study of aperiodic order. In particular, was a paper was full of ideas, maybe not completely rigorous from the mathematical point of view, but very influential, scaling properties of structure between quasi-periodic and random by Aubry, Godrèche, and Luc. And I know that Bert Hoff was influenced by that, and we in turn were using Bert Hoff's results in this direction. Well, so I should at least give some definitions. Since I'm talking about spectral measures, this is a general definition when we have RD action. So when we talk about substitution tilings in RD, we talk about the translation action and then assume that there is an invariant probability measure. So then the spectral measure corresponding to a test function is going to be a positive finite Borel measure on Euclidean space, which is given by this formula by basically the Fourier transform. So it's like a Koopman operator, and for maybe more familiar in ergodic theory are the spectral measures on the circle, but it's when you have just one transformation acting. Here, because we have RD action, then it's natural to talk about the spectrum living also on RD. In particular, the eigenvalues are really vectors or points on RD. And so here there's just a reminder of what eigenvalue means, that there is an eigenfunction. If we take the eigenfunction as a test function, then the corresponding spectral measure is just going to be a point mass. So this is completely general. When we talk about tiling spaces, we focus on finite local complexity tiling spaces. Then what are the natural test functions? Well, we call them transversely locally constant if they only depend on the patch of some fixed radius around the origin. The simplest kind of TLC functions are just characteristic functions of individual tile. So basically, let's say it's 1 if the origin lies in a tile of some particular type. Now, the precursor of the results I'm going to talk about is a joint work with Sasha Bufetov, which was published in 2014, where we worked with just one-dimensional substitutions. So let's say you have given a primitive periodic substitution, and well, as Natalie mentioned, the Pizot property plays an important role. So we assume that is non-Pizot in a strong sense, that the characteristic polynomial is irreducible over the substitution matrix, is irreducible, and the second eigenvalue is strictly greater than 1 in modulus. Then actually almost every substitution flow or tiling R action has spectral measures which are Hölder continuous with a uniform alpha. So away from 0, we always have to avoid 0 because at 0 you have a sort of trivial constant eigenfunctions. It's possible to avoid that just by looking at test functions of mean 0. So here the question is, what is almost every? Almost every is basically almost every choice of the tile length. Now one can ask, what about the self-similar flow? The self-similar flow is a special case when the tile lengths are chosen to be the Perron-Frobenius, the components of the Perron-Frobenius eigenvector for the matrix, so probably the left eigenvector, and then we get a weaker log-Hölder estimate. So it seems just very hard to do anything for the specific system. That's why we well, the result on Hölder continuity is only for almost every system. So this new work, the focus of today's talk is joint work with Rodrigo Treviño. And so we have a fairly recent preprint, Spectral Cocycle for substitution tilings. And well, there we extend this construction of spectral cocycle from the one-dimensional case that we did with Bufetov. And then we use it to estimate the Lyapunov exponents. But actually, as I mentioned, I probably won't have time to talk about it. Well, I should say that the motivation was basically to understand better the Rodrigo's paper. Rodrigo has a preprint from a couple of years ago, quantitative mixing for random substitution tilings. And there I should say that random is not in the sense of random substitutions that are being studied by Dan Rust and collaborators. It's random in a sense of S-adic system, that at each step you apply a different substitution. And the substitutions are taken from some ergodic process, maybe just IID from a finite number of substitutions. And so it's a fairly technical, but I wanted to understand, well, what happens in the simplest possible case when you just apply one substitution. And that's what we were starting to do. And along the way, looked at what, about the generalization of the spectral cocycle. So one thing we did generalize is basically because in Rodriguez's paper, he assumes that the expansion is a pure dilation. And we wanted to have more general expansion maps, in particular, allowing the irrational rotations. Now, when you have irrational rotations, then you inevitably have to work with fractal boundary of the tiles, as we saw also in Natalie's talk. But in order to consider, so we talk about deformations. And in order to have deformations, we need polygonal tiles. So then what we do is basically we pass to the pseudo-self-similar ones using Natalie's construction. Okay, so here is the result, which one of the results in our paper. In a sense, this is already in his special case of his result, except that we generalize it to allowing general rotations. And while we start with a pseudo-self-similar tiling space with expansion map phi, and assume that it has an eigenvalue which is greater than 1 in modulus, at least one of its conjugates is also greater than 1 in modulus, and is not an eigenvalue of phi. So then Lebesgue almost every admissible deformation, whatever this means, is going to be weakly mixing, but more importantly, has uniformly Hölder regular spectral measures. I should say that there is also an analog of the log Hölder result of Sasha and myself in the tiling, in the substitution tiling case, and that is due to Juan Marshall in his master's thesis. I don't think it has been published. So the question is, what about the deformations? Okay, yeah, because we talk about, yeah, so actually I may have missed something in my previous slide. Okay, yeah, maybe didn't appear. Yeah, all right. So, well, the question is, what about the deformations? What do we mean by deformations? In the one-dimensional case, things were pretty simple because deformations, as I said, is just varying the length of the tiles. Now, the deformations of tiling spaces have been studied by Lorenz and collaborators, and also by Johannes, and also the work of Johannes and Ian Putnam, very important here, using tiling cohomology. And so cohomology was also mentioned in Natalie's talk. Now, so what is our setting? We assume that the tiling space is FLC, uniquely ergodic, non-periodic, and all tiles are convex polyhedra meeting face to face. And how can we do it? And that's achieved via mutually local derivability using the derived Voronoi construction by Natalie. So even if we start with tiling having fractal boundaries, but so we lose exact self-similarity, but we gain the nice properties of the tile. But actually, in some cases, there is an obvious subspace of deformation parameters, and then we can just play with them without having to compute the cohomology. And so actually, I will now spend some time on this example. These examples are well known. These are examples of Kenyon's tilings. He introduced them in his GAFA paper in '96. It's an nice algebraic construction of pseudo-self-similar tilings using parallelograms. So I'll recall this construction. We start with 3 vectors in the plane, ABC pointing in different directions, and we look at the set of polygonal paths. Each path, basically, each side is a translate of plus minus A, plus minus B, plus minus C. And they can be concatenated by multiplied by concatenating and erasing in a backtrack. So this way we actually have a realization of the free group on 3 generators. So this certainly asks for a picture, and then there is a picture which actually, okay, no, before the picture we just start with a formula. So this is a substitution or endomorphism. So it comes from endomorphism of a free group. So we have a free group on ABC and define this endomorphism. A goes to B, B goes to C, C goes to C to the power P, A to the minus R, B to the minus Q, where P and Q are non-negative integers and R is at least 1. And then the basic tiles are parallelograms, commutator AB, BC, and AC. And it turns out that when you apply the substitution, so actually there is a natural decomposition. So A directly goes into B, and B goes into this formula, and actually it could be decomposed into several translated copies of C and B, and similarly for C. So that's what is written here, that each of the substitutions of the basic parallelograms ABC can be tiled by translates of ABC. In particular, if you have a commutator AR and C, can be tiled by R translated copies of AC. So the substitution matrix for this is easily computable, and this substitution can be iterated to obtain a parallelogram tiling of the entire plane. So I should mention that combinatorial substitutions like that have been considered by many authors, also by Shunji Ito and co-authors, by Michel Deking and Natalie and others. So the picture actually comes from my old paper, 97. So there I considered a special case when the parameters PQR are 0, 1, 1. So here you see the three basic parallelograms. So the first one, A, is A, B, A inverse, B inverse. It goes into capital B, which is B, C, B inverse, C inverse. And then B goes into this one. So this is the C parallelogram, C, A inverse, A commutator, which is mapped into A. But the substitution of B is decomposed into the two copies, translation of B and translation of C. So this is how the endomorphism acts on basic parallelograms. Okay, can you still see my slides? Hopefully yes. And this shows how this expands. This is I think what happens after 4 iterations. If you start with the B tile, we actually iterate first just the polygonal line, but then we decompose, and you see how the tiling is gradually fills the plane. So we continue a little bit with the general case. So there's natural polynomial coming with this, a cubic polynomial. So we need to impose conditions that guarantee that the polynomial is irreducible over the rational such as a complex root. It's fairly easy to compute. And if lambda is a complex root greater than 1 in modulus, then we make a special choice of ABC, 1 lambda lambda squared, and denote the resulting, consider the resulting parallelogram tiling. So this tiling actually turns out to be pseudo-self-similar with expansion given by multiplication by lambda. So it's a reminder that pseudo-self-similar means that it's locally derivable from its inflation. But we can actually obtain the genuine self-similar tiles, meaning geometrically self-similar with fractal boundary by iterating in rescaling. You apply substitution n times and then rescale by lambda to the minus n. The conversion Hausdorff metric to the fractal for each of the ABC. This idea was actually used in my paper with Natalie, where we show that any, pseudo self-similar tiling in the plane is actually mutually locally derivable, I believe, with the genuinely self-similar one and with a nice tile. So this is the picture still from that same old paper of what it looks like after rescaling, after blowing up and rescaling a few more times. Okay, Now, what about the conditions? So we are still working with the self-similar ones, no deformations yet. Well, we denote by XPQR the tiling space of this pseudo-self-similar tiling, and make this assumptions. Now, the dynamics, well, obviously are topologically conjugate on the parallelogram tiling and on the self-similar tiling because they are MLD, and they're weakly mixing if and only if this condition holds R greater than P plus Q plus 1. In fact, when lambda, when R is strictly less than P plus Q plus 1, you have a complex Poisson number, and then there is large discrete spectrum, which contains all integers in lambda as a subset of a complex plane viewed as a plane. In many cases, pure discrete spectrum was also confirmed there by Shigeki, Franz, and Jungyo Pli using algebraic coincidence algorithm. So when equality holds, the polynomial is reducible. So actually, I'm not exactly sure what happens there in terms of the tiling, because I think it still makes sense to consider the tiling. But for R greater than P plus Q plus 1, all the roots are outside the unit circle, so we have weak mixing. And so here are the few beautiful pictures. They are from the paper with Rodrigo, so you can see that, okay, he was the one making pictures. He's much better than me for this. So anyway, but actually, I think his student also was working on some of it. But anyway, you can see actually this looks like a stepped surface. So also something that Natalie mentioned. Really, this looks like a stepped surface. By the way, this is a 1-1-1, the complex Poisson case. So here it's known to be pure discrete. But you can ask what is the colors. The colors actually indicate the different types of colored tiles, not just the type of the tile itself. There are only 3 tile types, just the 3 kind of parallelograms like size of the cube. But here he actually records also the type of the neighborhood of the first corona of the prototype of the tile. So actually looking at this stepped surface immediately brings to mind how you do deformation. So for deformations, you can just tilt the surface, tilt the plane on which you project, and that gives a natural set of parameters. But or equivalently, you just change those vectors A, B, C. So here are a few more examples, a few more pictures. They are already weak mixing, 1, 1, 4, 1 to 5, 2 to 6. So now we'd like to start deforming them. So how do we deform them? As I said, here we, of course, it's a subset of this cohomology, but we focus on elementary deformations, which just correspond to perturbations of these vectors, 1 lambda lambda squared, which define the parallelograms. And there is a neighborhood, which you could sort of think about as a tilting the plane, or just looking at where the vectors point that parameterize non-degenerate deformations of parallelograms. So here we don't try to renormalize, we just work with the pseudo self-similar one and look at those deformations. So as mentioned here, can view them as stepped surfaces. And well, for each deformation, we consider the corresponding deformed tiling space. It's not hard to show that the translation action is uniquely ergodic, so it makes sense to ask about the spectral properties. So it's weak mixing, and well, it turns out that first let's talk about eigenvalues. That's the first thing. Actually, this was already essentially done in the work of Alex Clark and Lorenza. Except that they also assumed, I think, that there are no rotations, but their methods really extend directly to the case of pseudo self-similar tilings when the rotations in the expansions map are allowed. And in general, well, return vectors for a tiling play important role in understanding the eigenvalues. This already, I mean, this of course goes back to early work of Bernard Host on eigen discrete spectrum for just regular substitution. And here it's easy to see that the Z module generated by return vectors, okay, for the undeformed tiling is 1 lambda lambda squared. I mean, the module generated by the 3 generators. And what we do basically, we look at how the expansion map, recall, is multiplication by lambda in the complex plane. What it induces, of course, a linear map on Z3, and it's given by this matrix, which has exactly the characteristic polynomial we started with. So essentially, from the work of Clark and Sadoun, we get a condition for eigenvalues for this ergodic system, and it involves basically, we have to look at these perturbations of vectors 1 lambda lambda squared, take vector alpha, take the scalar products, and apply the power of the transpose of this matrix M and see if it goes to 0 mod Z3, then it's if and don't live condition for being an eigenvalue. Okay, and actually, well, the corollary, actually, this is the corollary of the result with Rodrigo stated at the very beginning, that if we are Wick mixing, in this situation, actually, we have not just Wick mixing, we have this quantitative Wick mixing, and that means that for Lebesgue, almost every deformation parameter, the action, I mean, the spectral measures are actually Hölder regular. Okay, so I believe that's actually all I wanted to say, and thank you very much.